Quadratic covariation. This is something we have for two functions, any two functions, f and g, on a time interval. The quadratic covariation of f and g is, perhaps you can guess what this is. We take the increment of f over a time interval and multiply that by the increment of g. And again, this is one of these limits that you take by subdividing the interval into a lot of short subintervals, and that limit is as the partition is refined. As you go to many greater and greater numbers of shorter and shorter intervals, this is the limit that you go to. One observation we could make straight away then is that the quadratic covariation of a function with itself is what we were just in the previous video calling the quadratic variation of f. So this is a bit like variance and covariance. When you have the quadratic covariation, you're putting two functions together like this. Now, this also you've probably never heard of, and there's an even better reason for this, because this also tends to be zero quite often for the kinds of functions you normally run into. In fact, if your f is a function of finite variation, and remember this is most functions, and g doesn't even have to be that, g is enough for g to be a continuous function on the interval 0 to t, the closed interval 0 to t, then that's enough for the quadratic covariation to be 0. And it's not even very difficult to show that. Basically, g being continuous means that over short enough time intervals its increments will be small. And then, if you think of this as always being something small, bounded above by a small constant, so take it out and you're left with just the total variation of f, which we've said is finite. So I won't bother to outline that in any more detail, we'll just take that as a fact. What that means is that any time we have stochastic processes let's write them as stochastic processes xt and yt, so these are random functions now. When are we going to have their quadratic covariation being 0? Well, one time when it will be 0 is if either one of them, either x or y, is a finite variation process. So if either one of them is a relatively smooth function, i.e. not a typical Ito diffusion, then the quadratic covariation will be 0. That then leaves us with the question of, well, what if we have two more typical Ito diffusions? What's their quadratic covariation? Then perhaps we'll get something that's not 0. One other fact to note just before we go any further. The quadratic covariation of f and g squared, that is, you find the quadratic covariation first and then square it, is less than or equal to the quadratic variation of f times the quadratic variation of g. So if you've got a couple of typical Ito diffusions, we know that for those the quadratic variation of them is a finite quantity always. So if you've got two of them, what this tells you is that their quadratic covariation will be finite as well. So for typical Ito diffusions, actually for any Ito diffusions, but in particular for typical ones like Brownian motions, the QCV of any two of them will be a finite quantity. Why is this true? If you've seen things like this before, you might be able to guess where this comes from. It comes from something called the Cauchy-Schwarz inequality. Which is this, that if you have a sum like this, sum of AI, BI, this is for any numbers, AI and BI can be just any numbers at all, the sum of their products, all squared, is less than or equal to the sum of the A's squared times the sum of the B's squared. Useful thing if you've ever run into that before, and then taking this as given, you can probably see how this immediately gives you the result for the quadratic covariation, because those A's and B's are just like the increments of the two functions, the F's and the G's. The quadratic covariation comes out to be 0 quite often, which is useful. One other case when it comes out to be 0 is if you've got two Ito diffusions that are independent of each other. It's a bit like two independent random variables having a 0 covariance. Two independent Ito diffusions have a 0 quadratic covariation. So let's just see why that is. And as with these other derivations that I've been doing, I'll do this only for Brownian motions. So this is for independent Brownian motions. Wt, and what shall we call the other one? Wt prime. If you want, you can, as an exercise, go through these arguments for the general Ito diffusion instead of just for a Brownian motion. If you try that, you'll find that it's essentially the same, but with more writing to keep track of everything. So what have we got? We've done this a couple of times already now. We've got our interval from 0 to t. We subdivide it in half, and then in half again, and then in half again, and so on. We do that n times. So now we've got time points from tn0 to tn 2 to the power n. And what are the increments? That's the increment of w is what we'll call again Zni. That's a normally distributed random variable with mean 0, and its variance again is the elapsed time, t over 2 to the n. And we've got the same for the other one, for w prime. Except that, of course, it's not exactly the same. These are different random variables. Let's call these ones y and I. And they also have this distribution. So we've got all these z's, these are all independent random variables, and these y's, these are also all independent random variables, and they're independent of each other as well. There's independence between the z's and the y's, and that was the crucial thing we assumed at the start. So then what does that tell us about the quadratic covariation of w and w prime? We're looking at the limit, n goes to infinity, so now it would be the sum at the nth stage of approximation. We have 2 to the n terms, and it's one increment times the other increment. Increment of one process times an increment of the other process. Okay, again, now we've got something like a great big sum of independent random variables here, so we should be able to turn that into something like a sample mean. So let's see, we've got, now what are these guys individually? Well, we should divide them by their, we should scale them to make them come out right. So how about we do z in I divide by its, doesn't make a lot of sense to divide by its mean because that's 0. How about we divide by its standard deviation? And same for the other one. And we also want to have a 1 over 2 to the n here so that we're dividing the sum by the sample size to get a sample mean. That makes all of the 2 to the n's cancel out nicely, so the only other thing I need to put in to make this right is a t. Okay, now what have we got? We've got a sample mean for a sample of size 2 to the power n. And what are the things in it? Well, we've got this guy. This is a z in I with this distribution, and we've divided by its standard deviation, so this is now a standard normal. And so is this. So what we've got here is two independent standard normals being multiplied together. And then whatever distribution you get when you take two independent standard normals and multiply them together, that has a certain distribution. It's not a named distribution, I think, but it is a distribution that it has. That's the distribution we're sampling from, and we're taking a sample mean from that distribution. So what it should converge to will be the population mean, that is the expectation. So the whole thing, this whole sample mean, should now converge to expectation of, z prime, where z and z prime are independent standard normals. Okay, and therefore the limit of the whole thing is whatever this expectation is times t. But what is this expectation? Well, in fact, because they're independent, it just splits up like that, and each of these expectations is 0. It's the expectation of a standard normal. So we've got a 0 times 0 here, so final answer for the whole thing, 0.